In this lesson, we're going to look at the combined gas law. So if we don't change how much gas we have, so the mass or number of moles of gas remains constant, then the three laws which we have looked at, which are Boyle's law, Charles' law, and Gay-Lussac's law, those can be combined into one relationship. So we had P1V1 equals P2V2. And we had P1 over T1 equals P2 over T2. And we had V1 over T1 equals V2 over T2. So we can see here that in all of these, pressure and volume are in the numerator and temperature is in the denominator. We did see that within each of these relationships where we had denominators, we could flip them if we wanted to, but for the purposes of here, pressure and volume are in the numerator, temperature is in the denominator. So the combined gas law would be P1 V1 over T1 equals P2 V2 over T2. So the initial pressure times the initial volume divided by the initial temperature is going to be equal to the final pressure times the final volume divided by the final temperature. So once again, in this case, if we were looking for a temperature, we could take this relationship and flip that. So T1 over P1 times V1 equals T2 over P2 times V2. So once again, super important, this is when temperature is in Kelvin. So we have to make sure that we are always converting that. Okay, standard temperature and pressure and standard ambient temperature and pressure. So because the volume of a gas varies with temperature and pressure, it can be helpful to have some reference points to compare gases. So the standard temperature and pressure, STP, standard temperature and pressure, and SATP, standard ambient temperature and pressure. Those are, so STP happens at 0 degrees Celsius or 273 Kelvin and 101.3 kilopascals. So this is the original standard that used to be used, STP, so at 0 degrees Celsius. And then they realized that it's not particularly great to be working at 0 degrees Celsius, and most buildings are not kept at 0 degrees, but are kept in the low to mid 20 degrees Celsius, which we refer to as room temperature. And so SATP, standard ambient temperature and pressure, is 25 degrees Celsius or 298 Kelvin and 100 kilopascals. So if I have a gas at 110 kilopascals and 30 degrees Celsius, and at that point, the container takes up to 2 liters of space. And then the temperature rises to 80 degrees Celsius and the pressure increases to 440 kilopascals. What would be the new volume? So pieces of information I have are, actually before we do that, we're going to do conversions to Kelvin. So our initial temperature was 30 degrees Celsius plus 273 is 303 Kelvin. Our final temperature is 80 degrees Celsius plus 273 is 353 Kelvin. So we had, over here, so we have our initial pressure and initial temperature, which we've converted to Kelvin further down, and initial volume. And then our final temperature, which we've converted to Kelvin, and our final pressure. And then we're going to be looking for our final volume. So there's our relationship, P1 V1 over T1 equals P2 V2 over T2. So we can plug in all those pieces of information that we have. And to solve for V2, so 400 kilopascals is multiplying by V2, so I'm going to need to divide that. So that's going to end up in the denominator. And this is a division by 353 Kelvin, so I'm going to multiply that. So that will end up in the numerator. So I've got kilopascals and kilopascals, Kelvin and Kelvin, so my final answer will be in liters. And once I plug that into the calculator, that gives me 0.64 liters is how much that gas will take up at the end. Another example, so a gas at 110 kilopascals and 30 degrees Celsius fills a container at 2 liters. What volume will the gas occupy at STP and at SATP? So we're first going to convert our temperatures to Kelvin. So STP, 30 degrees Celsius was 303 Kelvin. And at the beginning for part A, our temperature is 0 degrees Celsius or 273 Kelvin. So I have my initial pressure and initial temperature, initial volume. Then I have my final temperature and my final pressure. So STP pressure is 101.3 kilopascals. So that's a standard that's given. So I'm going to plug all of those values into the formula. And once again, I'm looking for a volume, so I'm going to divide by this. That's going to move that into the denominator. I'm going to multiply that, which will move it into the numerator. So kilopascals, Kelvin, my final answer will be in liters. So that is equal to 1.96 liters. And then to convert to SATP, there my final temperature would be 298 Kelvin and my final pressure would be 100 kilopascals. So once again, we can plug in everything that we know. Same thing, we're going to divide this to move it over, multiply by this, and those all cancel out again, so we'll have liters again as our answer. And at SATP, that gas would take up 2.16 liters.